Cramer's rule provides us with the following formula for the inverse of matrix A. So if we let A be an n by n invertible matrix, then the inverse of A can be found by 1 over the determinant of matrix A multiplied by the adjugate of A. We can rewrite this as the adjugate of matrix A by the determinant of A. And this is where this ADJ of A is called the adjugate matrix. And what the adjugate matrix is the transpose of the matrix of cofactors of A. So we can say the adjugate of A is the transpose of the matrix of cofactors of matrix A. So this formula by Cramer's rule can be used to find the inverse of A. So to better help convince us that this formula works, I want to go ahead now and derive this formula using a 2 by 2 matrix, since we know that standard formula of A already. So let's take a look. So in finding the inverse formula by Cramer's rule, we start by recalling our 2 by 2 definition of an invertible matrix. So if A is defined by the 2 by 2 matrix ABCD, and the determinant is not equal to 0, then A is invertible, and the inverse formula is defined as 1 by the determinant of A multiplied by the 2 by 2 matrix A negative B negative C D. And so some of the resulting questions from this formula is, can we use this formula to find an inverse for a 3 by 3 or even an n by n? So let's try to verify this formula using our 2 by 2. So we can make a couple of assumptions pretty safely right off the bat. The first is that it's safe to assume that this formula is going to contain 1 by the determinant of A. Now, from our more recent knowledge of the properties of a determinant, it's safe to assume that it's also going to include cofactors. So what we want to do now is find a matrix of cofactors for A. So again, we're still using this general matrix A, B, C, D, and we want that matrix of cofactors. So you want some matrix C defined as C sub 1, 1, C sub 1, 2, C sub 2, 1, and C sub 2, 2. And so to do this, let's recall our cofactor definition from 3.1. So let's recall that the cofactor in the ith-jth entry, the cofactor of the ith-jth entry is determined using the formula negative 1 to the I plus j multiplied by the determinant of the submatrix A sub ij. So the submatrix obtained by eliminating the ith row and jth column. So let's find our cofactors. So we need the cofactor in the first row, first column. So that's negative 1 to the 1 plus 1 is 2, multiplied by the determinant of the submatrix A sub 1, 1. So we're left here, so negative 1 squared becomes positive 1, multiplied by D. So we're just left with a cofactor in the first row, first column as D. And we'll keep in mind here, in case you think, where did this D come from? Is that math magic? Remember, with our cofactor expansion here, to find that submatrix, we're thinking about the entry in the first position, or first row, first column, and we eliminate the adjacent row and adjacent column, which just leaves us with D. And we do the same thing for the other cofactors. So I have the cofactor in the first row, second column, which is negative 1 to the 1 plus 2, So 3 multiplied by the determinant of the submatrix A sub 1, 2. So this is equal to negative 1 multiplied by C, or just negative C. So we have the cofactor in the second row, first column. So that's negative 1 to the 2 plus 1, which gives us 3 multiplied by the determinant of this submatrix, A sub 2, 1. So we're left with negative 1, and then the determinant of this submatrix is B. So I have negative B. And last but not least, the cofactor in the second row, second column. So we have negative 1 to the 2 plus 2, which is 4, multiplied by the determinant of the submatrix A sub 2, 2. So negative 1 to the fourth becomes positive 1 multiplied by A, or simply A. And so what we have here is our matrix of cofactors, defined by the 2 by 2 matrix, C sub 1, 1, C sub 1, 2, C sub 2, 1, C sub 2, 2. And so plugging in what we found, we have D minus C minus B, A. So here is our matrix of cofactors. And if we now take the transpose of this matrix, so if we interchange the rows and columns, so we have C sub 1, 1, C sub 2, 1, C sub 1, 2, C sub 2, 2, we are left with our familiar matrix, D minus B minus C, A. So again, this confirms the inverse formula for our 2 by 2 matrix to be 1 by the determinant multiplied by a matrix of, multiplied by the transpose of the matrix of cofactors. So we generalize this for any n by n invertible matrix with the inverse formula by Cramer's rule. Which is A inverse 1 by the determinant of A multiplied by that matrix of cofactors, and we call that matrix of cofactors the adjugate of A.